Hello, in this video we'll be looking at some trig manipulations. So essentially what we are doing here is looking to see how if I give you the value of say cos of theta, sine of theta, tan of theta, one of those things, if you could figure out the values of the others using that. So for example, suppose I tell you that cos of theta is a half or cos of theta is a third. And I ask you, well, what is the value of sine theta? So that is what I mean when I say manipulating trig expressions. So hopefully after this you'll be able to work that out. Now there are two things that we will discuss. The first is using identities to do this, and the second is using something called the magic triangle trick. Okay, so when using the identities to do this, it is important to know what quadrant the angle lies in. Right, so the argumentator, what quadrant does it lie in? Does it lie in the first quadrant, the second quadrant, third quadrant, or fourth quadrant? So if it's in the first quadrant, meaning theta is between 0 and 90 degrees or pi on 2, then all three of these are positive. Cos theta, sine theta, tan theta are positive for any angle theta that is between 0 and 90 degrees. If it's in the second quadrant, meaning the angle is between 90 and 180 degrees, then only sine theta is positive. The other two are negative, cos theta and tan theta. If it's in the third quadrant, then only tan theta is positive. The other two, sine and cosine, are both negative. And finally, for the fourth quadrant, cosine is positive, but sine and tan are negative. Alright, just note that the remaining three expressions, secant, cosecant, and cotangent, since these are the reciprocals of cos theta, sine theta, and tan theta respectively, then they would have corresponding signs, meaning if cos theta were negative, then secant theta will also be negative. And the same for the others. So this is just representing the different quadrants and which angles or which expressions are positive or negative. So most of you may remember this trick. So the trick is ASTC, right? All first quadrant, all are positive. Second quadrant sine, third quadrant tan, and last quadrant cosine. All right. So if we have an expression for some trig function and we know which quadrant it lies, the angle lies in, meaning what interval the argument is in, then we can find expressions for the remaining functions using standard identities. Right, so the standard identity, sine squared theta plus cos squared theta is equal to 1, and the corresponding identities for the others. So here in this identity sheet, you can see some of the identities that I'm referring to. So cos squared x or theta, whatever it is, plus sine squared x is equal to 1. We have two other identities here, which are also pretty useful when we will be doing this. Okay, so this is an example I have here. So let x and y be related by this equation. So sine of y is equal to x over 3. So this is an equation relating x and y. Meaning whatever the value of y is, sine of that is going to be equal to the value of x divided by 3. Now, given that the angle inside here, y, the argument y, is between 0 and 90 degrees, I want you to find expressions for all the remaining trig functions. Right, so I gave you sine of y, so I want you to find cosine of y, tan of y, cosecant y, secant y, and cotangent of y, all in terms of x, because remember, if sine of y is in terms of x, then all of these will be in terms of x. Alright, so the most obvious one is if I give you sine, then you can find cosine using this identity. Sine squared plus cos sine squared of the angle plus cos squared of the angle is equal to 1. And remember, when it's in the first quadrant, everything is positive. So using this identity, we can rearrange and make could rearrange and make cosine of y the subject of the formula. Now, why it's important to know the sine or to know the angle, is when I make cosine of y the subject of the formula, I'm going to have to take the square root. And when you take the square root, you have to determine whether it's a positive square root or the negative square root. And how you determine that is from the quadrant. Remember, if the angle is in the first quadrant, cosine is supposed to be positive. Meaning in this case, I have to take the positive square root. Right? If it were, for example, in the second or third quadrant, I would have to take the negative square root because it's supposed to be negative in these quadrants. For the fourth quadrant, it is again positive, so you would take the positive square root. Right? And that is why we need to always know what interval we are looking at or what quadrant we are dealing with. So, cosine of y from this identity is equal to the square root, the positive square root of 1 minus sine squared y. Now, we know what sine of y is, so we can simply substitute that. So we get the square root of 1 minus x over 3 all squared. Right, now you can simplify this a little more. So this would be the square root of 1 minus x squared over 9. I can write it as a common fraction, so it would be, if I have 9 as a denominator, it would be 9 minus x squared over 9. And then I can take the square root of the numerator over the square root of the denominator. The reason being, square root of 9 is 3. Right, the reason why I simplified it like this here is because it'll help for the other expressions or the other functions we need to determine. Now, once we know what sine and cosine, what those values are, then we can find tan of y, because remember, tan of the angle is sine over cosine. Right, so this is another one we will often use. So we take sine of y, which is x over 3, divided by cosine of y, which is this expression that we just found here. Now the 3 will cancel, and this 3 will cancel with this 3, and we end up with x over the square root of 9 minus x squared. Right? If I had not simplified this like this, then this would have been a bit more complicated here. Right? And then once we have sine, cosine, and tangent, the remaining 3 are just the reciprocals of these. So I just need to take those reciprocals. So cosec is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tan. So I've found the remaining 5 function values. So cosine, tan, cosecant, secant, and cotangent. And that's basically it. You simply use the identity that you need. In this case, we use this identity first, then this identity second, and then these for the reciprocals. We simply use those to get the desired values that we need. Alright, now once we understand how to do that, we could look at a couple more complicated problems. So here x and y are related by this equation. So this time we don't just have like y inside here, we have a third y squared. So we have a cosine of a third y squared is equal to 2x. Given that everything inside here, meaning a third y squared, is between 0 and 90 degrees, find an expression for tan of a third y squared in terms of x. Now this might seem a little complicated because it's a third y squared, right? It's not just y. But if it'll help, you can use a substitution. You can let, for example, z equal to a third y squared. Then we have cos of z is 2x. I know that z lies between 0 and 90 degrees. And I want to find tan of z. Right? It's much more straightforward that way. Right? So it doesn't matter what the angle is. I know that the entire angle lies between 0 and 90 degrees. Then I can proceed to use my identities, and I know if I ever have to take a square root, it's going to be positive square root because all of them are positive in the first quadrant. So, but how do we do this? How do we get tan of a third y squared given, or tan of anything given the cosine? So we could look at the available identities. We need an identity relating tan and cosine. Now, there is one here, but this has sine as well, and we don't know what sine is. Now, I could, if I wanted to, use the identity cos squared plus sine squared is 1 to find sine of this angle, and then divide to get tan. So that's one way we could do it. And I encourage you to try it that way and make sure you get the answer that we got later down. The other way we could do it, which is how I will do it, is we know cosine, so we could find secant. Remember, secant is 1 over cosine. Right, that's easy to do. We just take the reciprocal. And then using this identity, secant squared is 1 plus tan squared, we can just make tan the subject of the formula and get our answer. Right, so secant of the angle is just 1 over cosine of that angle, so 1 over 2x. And given that the angle is in the first quadrant, then tan has to be positive, so we can use this identity here, make tan the subject of the formula, so we'll get tan of x is the positive square root of secant squared x minus 1. So we have the positive square root of secant squared of the angle minus 1. Now we know secant of the angle is 1 over 2x, so secant squared is going to be 1 over 2x squared. Alright, now again, I went on to simplify this here. So what we do first is this will, inside the square root, we have 1 over 4x squared, and then minus 1. We can write this as a common fraction. So we'll have 4x in the denominator, and I'll get 4x squared in the denominator. I'll get 1 minus 4x squared on top. And the square root of 4x squared is 2x. And we are left with the 1 minus 4x squared inside the square root on top. And that's all there is to it. So once I give you a trig function of an angle, I am expecting that you should be able to use your identities to be able to find some other trig function using that same angle. Alright, one last one here. This is a bit more complicated. Alright, so x and y are related by this equation this time. Cotangent of the hyperbolic sine of ln of y squared minus 1 is equal to x. So given that everything inside this cotangent, right, you could think of everything inside here, sinh of ln of y squared minus 1, think of that as some angle z. Given that z, that angle, lies between 0 and 90 degrees, find an expression for sine of z, right? Again, this is the entire angle here. Right, so ignore the thing inside. Like I said, this is just an angle. It doesn't matter what this is. All we are concerned with is what is this trig function and what do I need to find. So the trig function is cotangent and I need to find sine. Well, how do I do that? So we know cotangent is 1 over tangent, so I could find tan of this angle, which would just be 1 over x. But that doesn't directly help me with sine. I still need to do something else. Right, now we don't know cosine in this case, so we can't use this to help. What do we have? We have cotangent. Now, if you look at this identity here, remember cosecant is 1 over sine. Right, I want sine. So I could use this identity to find cosecant and then take the reciprocal to get sine. Right, notice I have CSC here and cosec here, they're both the same thing. Usually cosecant is abbreviated CSC, but sometimes it's also used as COSEC. So we'll do that. So first of all, the angle is between 0 and 90 degrees, so cosecant of the angle is positive. We can take the identity mentioned and make cosecant the subject of the formula by taking the positive square root of both sides. So cosecant is the positive square root of 1 plus cotangent squared of the angle, so it's just the positive square root of 1 plus x squared. And to get sine, we just take the reciprocal of cosecant, so the answer is just 1 over the square root of 1 plus x squared. Alright, and that's all there is to it. Now the second method, there's a second method that you can use to get the exact same things we got before using a different approach, which is called the magic triangle trick. So with this trick, we are not going to use any of these identities. Right? If anything, we'll use this one sometimes, but not really. What we will be using is the fact that if you have a right angle triangle, right? So I have a right angle here. Suppose this angle is theta, then we can determine sine, cosine, and tangent of that angle theta in terms of the sides of the triangle. So everybody should remember SOHCAHTOA. Sine theta is opposite over hypotenuse. Cosine theta is adjacent, meaning the one alongside the 90 degrees, not the hypotenuse. Adjacent over hypotenuse. And then tangent is opposite over adjacent. Right, so we'll use this idea. And I'll use a simple example to illustrate that. Suppose I tell you again, this is the first example we looked at, but a slightly simpler version. We only need to find two of the functions. Suppose I tell you again that sine of y is x over 3. Given that y is in the first quadrant, find expressions for cosine y and tangent of y in terms of x. Right? So remember, sine is opposite over hypotenuse. So imagine I had a right angle triangle and the angle was y. Then the opposite side length divided by the hypotenuse should be sine of y, which is x over 3. Right? So let me come back to this first. So the opposite over the hypotenuse is supposed, after you simplified it, it's supposed to be x over 3. Now, you can create any right angle triangle where this divided by this, the hypotenuse, the opposite of hypotenuse, is x over 3. It doesn't matter how big it is, as long as the ratio is the same. Then the angle here will always be y. Right? It will always be the angle we want. And then using that triangle, we can determine any of these by finding the third side using Pythagoras' theorem. Right? Remember, right angle triangle. The third side here, the adjacent side in this one, would be the square root of hypotenuse squared minus opposite squared. Right? Same thing for the opposite, square root of hypotenuse squared minus adjacent squared. Now the hypotenuse would be the square root of opposite squared plus adjacent squared. Right? So it's just Pythagoras theorem. So we can use that. So what I can do is create a triangle. Now there are infinitely many triangles that would satisfy this. I just need to find a triangle where the opposite, when I divide the opposite side by the hypotenuse, I get x over 3. The easiest thing I can do to do that is to let the opposite side be x and then the hypotenuse be 3. Because if the opposite is x and the hypotenuse is 3, when I divide them, I will get x over 3, which is what I want. Alright, so we draw a right angle triangle such that y is one angle in that right angle triangle. Not the right angle, obviously, it's another angle. Since sine of y is opposite of hypotenuse, we can let x be the opposite and let 3 be the hypotenuse, because we know we want x over 3. So x is the opposite side of this angle, and then 3 is a hypotenuse opposite the right angle. So we created a triangle like this. Now you can sketch any triangle, not drawn to scale, put down these lengths here, x and 3, and then you can work out using Pythagoras' theorem the third side. So again, this is going to be the square root of the hypotenuse squared minus x squared. So the square root of 9 minus x squared. Right, and then once we have this triangle, I know what sine of y is, right? Right, sine of y is x over 3. Once I have this triangle, I could find cosine of y. Cosine of y is adjacent over hypotenuse, so it's just going to be the square root of 9 minus x squared over 3. And similarly, tan of y is opposite over adjacent. Sorry, opposite over adjacent. So x over the square root of 9 minus x squared. Right? You can simply write those down because of the fact that you know what the angles are, what these functions are in terms of the side lengths. And also you can double check that these were the same values we found up here when we did it using the identities. Right, cosine of y, square root of 9 minus y squared over 3, and tan of y, x over the square root of 9 minus x squared. Right, same expressions here. Right, so this, generally speaking, when I have to work out, do some trig manipulation like this, I usually prefer the magic triangle trick. Now you don't even need to draw the triangle. Right, you can just say let x be the consider a triangle such that x is the opposite side and 3 is the hypotenuse, then y is the angle, and then using Pythagoras' theorem, you get the third side. You could do that. Of course, it'll be much less explaining to do if you draw the triangle. If you just simply draw the triangle, put down the sides, and write down what this is, then you don't need to explain all of that, right? You can easily see from the triangle what these work out to be. So this is, I think, yeah, this is a question we had looked at before, but it was done using identities. So now we could do it using the magic triangle trick. So we know cosine of this angle is 2x. All right, now remember cos is adjacent over hypotenuse. Now there's no fraction here, right? It's just 2x. But you could think of anything, any number or any value as a fraction. The denominator is just 1. Right? So you could let 1 be the denominator, so you have 2x over 1, and then 2x will be the adjacent and 1 will be the hypotenuse. So you draw a triangle where the hypotenuse is 1, the adjacent is 2x, this is your angle here, and then you can work out the remaining side. This will be the square root of 1 squared minus 2x all squared. Right? So, and then once I know what that is, I can work out tan of the angle. Tan of this angle is opposite over adjacent. So it will be square root of 1 minus 4x squared over 2x. Alright, notice there's no real calculations being done here besides this working out using Pythagoras' theorem. Whereas before, with the identities, you might have to do some calculations. This is really just explanations. Now, if you are using this approach to solve a problem, you don't need to explain all of this, right? All of this here is just to explain it to you all. You could just simply say, consider this right angle triangle, and then using Pythagoras' theorem, we get the third side. Hence, it follows. Hence it follows that this is our answer. And then finally, this one again we had considered before. So what we can do is draw a triangle where, now we have cotangent, right? Cotangent is x, so that means tangent is 1 over x, right? It might be a little tricky to consider cotangent, so you might first want to think of it as tan of this angle is 1 over x. Remember, tan is opposite over adjacent, so therefore you can let the opposite side be 1 and the adjacent side be x. Right? And this is your angle down here. And then the third side, using Pythagoras' theorem, will be the square root of 1 squared plus x squared this time. Right? Plus because we calculated the hypotenuse, which is the longest side. Right? In this explanation, I just left it cotangent, but you might prefer to use tangent instead. But anyway, once we have the triangle and we have all three sides, I can work out sine of this angle. Sine of this is going to be opposite over hypotenuse. So it's just going to be 1 over the square root of 1 plus x squared. Again, there's no real calculations here. The only calculations is going to be done up here when we use Pythagoras' theorem. And that's that. It's really straightforward. So I hope that you all will take the time to go through this and understand the methods, both methods. Whichever one you choose to use is up to you. Just make sure you understand how to use it and it should be good to go. Alright, so that's it for me. I will end this video now. Bye.